So the point of this video is to talk about electric fields. And the biggest distinction I want to make immediately is notice there's a difference between electric field. So the point of this video is to talk about, my bad. There's a distinction between the electric field and the electric force. And I want you to to draw an analogy here. I want you to think about the force due to gravity. When we were talking in physics 161, oftentimes we would say mg. Now that's not a vector, but we could make this into a vector if we say it's this in the negative r hat, meaning towards the center of the Earth. And just to clarify that, maybe I'll bring out my globe really quick. The idea here is, you might be saying, wait, isn't it negative j hat? But yes, remember at different spots on the planet, gravity is pointing radially inward. Sorry if that arrow's drooping a little bit there. But the idea is, technically, we should really be saying the force due to gravity is towards the center of the Earth. So that's why I'm using negative r hat instead of negative j hat. All right? Now, in this case, we could actually group these two items together, the g and the direction, and that would actually look like, we could rewrite this force in this way. Force due to gravity is equal to mass times g, vector. And it turns out the g vector could be called the gravitational field. It's not the force, but rather the force per unit mass. And obviously, this is only valid near the Earth's surface, because we know that as you go up in altitude, g will change. But it's good enough for this. It's the force per unit mass. So that's what a field is, right? It's the direction and magnitude at every point in space of this quantity g. All right? Why am I bringing this up? Well, take a guess. It turns out the force electric, and maybe we'll put a subscript E on here for an electric force, is equal to some amount of charge times the electric field. All right. And so just like the gravitational field is the force per unit mass, we see that the electric field can be thought of as the force per unit charge. It's a little bit trickier, however. I want to point out gravity is always going to be attractive. So the field is always radially inwards and the force is always radially inwards. One significant difference would be, think about what happens when you multiply by a negative charge. If the electric field was pointing in some particular direction, the force would be the opposite direction if you use a negative charge. So let me summarize that with two bullets. So how about I say it like this way? If Q is greater than 0, force E points same direction as the electric field. However, if Q is negative, we get an opposite direction. So positive charges will move in the direction of the electric field. Negative charges will feel, I should be careful. Positive charges feel a force in the same direction as the electric field, whereas negative charges will feel a force opposite the direction of the electric field. Now, again, you might be saying, well, how does this relate to this analogy here, right? When I throw a marker up in the air, while it's moving upwards, the force is downwards. So that's why I corrected my language here a little bit. Obviously, just because the force points in one direction, that's not necessarily the direction it's moving, but that is the direction it's accelerating. All right. Now another distinction here, all right, and I want to point this out with this analogy. The gravitational field was caused by a mass, typically the mass of the Earth or whatever planet or moon you're on, right? So to be clear here, this G was caused by one mass. And so this is the mass that experiences the force, and this is the mass that's causing the force, or this relates to the mass that's causing the force. Similarly, up here, right, we know that forces come from pairs of charges. So when we're using this equation, let's do it like this. The charge sitting out front is the charge that will experience the force. A different charge creates the field. So notice how crucial it is that we use force and field correctly, all right? So there's going to be one charge that creates a field and another charge that experiences it. Now, to give you an idea, and maybe to just show you that this is kind of cool, I've got some different simulations here I want to share with you. So let's take a look. Let's look at this one here. This is showing a typical electric field. So notice I have a bunch of arrows on the screen. Now, to simplify this, maybe I'll take all those arrows out for a minute and bring them back in a second. So let's say I have two charges. Oh, actually, let's start with just one charge, okay? So let's say I have a positive charge sitting out here. Imagine I wanted to place another charge right here. So let me simulate this with this mode here. So let's pretend I wanted to put a charge here. This is going to be called my test charge. If you read a book, oftentimes they'll call this a test charge. And sometimes the test charge is given the symbol Q naught for no good reason. All right. The idea is if Q naught is positive, let's think about it. There would be a force directed away. That's the direction of the force. Well, since I know this charge is positive, I know the force and the field associated with the electric Coulomb force point the same way. So this is the direction the force would be if the test charge was positive. Therefore, this is the direction of the electric field, right? If I put it in a different spot, the electric field would be this direction. Now think, this second one that I drew is a little bit closer to the plus charge. We know from experience, the closer the charges are together, the larger the force. Remember, the force equation for two charges, just the magnitude, was K, Q1, Q2, all over the distance between them squared. So think, in this case, if we are closer to the charge, we should have more force. Therefore, we also should have more field. So this one's probably going to be a little bit longer. The idea here is there's an electric field at every single point in space, even though you don't put a charge there. The electric field exists, and then what happens is we can calculate the electric field at every point in space, then we know if we put charges in those locations, it's very quick to get the force. Now, if you recall, the electric field is the force per unit charge. And this is sometimes why they use that Q naught. We like to clarify whether we're dividing by the source charge or this test charge. And so the electric field should really be the force divided by the size of the test charge. Now, if I look at this equation on the far left here, I could see that this is going to look something like this. K, the source charge, I'll call that Q source. There's going to be some distance, and maybe I'll square that. And then there's going to be an R hat. So if we include the vector. And so this gives us the equation for the point charge electric field. That's a big result. I'll summarize this on the board in just a minute. And just so you can see this maybe a little bit neater, let me clear off some of this junk. And now we can actually use the simulation. This sensor that I'm going to put out here is like a test charge. When I put it here, we pretend that this yellow sensor is a positive charge. And look what happens when I release the mouse right now. That shows us the direction of the electric field. Whereas if I go here, think to yourself which way the electric force should point. If that yellow is a plus charge, the force should be upwards. Therefore, the field is upwards. Whoa, notice it's a lot bigger. And so that's related to this 1 over r squared. But we could do this at all kinds of different points. And so as we go around a plus charge, we see there's an electric field. And depending on if you get too close, you can't see it all. The closer you are, the bigger the field. And it points radially away from the plus charge. That's why there's an R hat in that equation. All right, so let me get rid of this. Let me restart this. What if we used a negative charge? Whoops. If we use a negative charge, well, you probably already saw it. I just want to point something out right here. If you put in a negative sign right here, that effectively is going to be negative R hat direction, so radially inwards. So now, when I put these sensors around, we see that the force points into, and as I get closer and closer there, or farther and farther, you can get an idea. Far away, the field is small and radially inwards for a negative charge. And just so I can see this, I'm going to move these a little bit. So notice the field towards a negative sign is radially inwards. The field around a plus charge is radially outwards. Now it gets tiresome putting out a sensor for each one of these, so I'm going to clear that off. And I'll put out a plus charge here, and then I'm going to click this button. This is showing a whole bunch of vectors. And notice in this case, they made all the arrows the same size, but as you get farther away, they become more transparent, or they have lower opacity. And it turns out in a couple of weeks, you can actually make this code yourself, and I'm going to help you do that in lab. So we'll learn more about that. So there's a plus charge, and I'm going to put that way over here. Here's a minus charge. And now notice what happens. We can actually use what's called the superposition principle. And maybe I'll write this up on the screen here. Give me just a sec. The superposition principle says that E total is equal to the sum of each different electric field. So we could have E1 from the plus charge, say, and we could have E2 from the negative charge. So what's cool about this is we could actually use this formula that you see on the top right for the electric field for each point charge separately, figure out the R vector and get r hat for each different charge, plug in the sign of the charge, and we could get the net electric field, which is actually shown right here. And obviously, the closer you get these things together, watch what happens here. Some interesting stuff. The field is going to be crazy strong in between, right? If I put one of these in there, you can see what I mean. It's like bonkers huge. But outside, it falls away quickly, right? And the closer these charges are together, think if we put them right on top of each other. Outside, there's almost no electric field, right? And the idea is the superposition principle tells us if the two charges are exactly on top of each other, the field should cancel entirely, right? We don't see anything anywhere. And that's because the electric fields exactly balance out. All right, so hopefully what we can do is learn how to do some math and figure out the electric field at one point in space on paper. And here's the big picture, right? If you can figure it out at one point in space, then we can tell the computer that formula and have it draw the arrows at every point in space. So we learn how to do this for one point in space and then make the computer draw it at every point in space. And then just for kicks, electric fields and gravitational fields are not the only types of fields. Here's another cool one just to look at. This is showing a wind field. It's another type of vector field. And notice when we zoom in here, that's approximately where we're located. Not exactly. I just want to point out, this is a lot like the electric field, only now the velocity of the wind has a different size and direction at each point in space. And so if we look at, oh, let's look down here. It's always fun. Whoops. Whoops. I always like to look down here. This is always cool too. There's usually some gnarly winds down here. So that's a polar view there. But the idea, just like the electric field has a magnitude and direction at every point in space, we see that the wind has a different direction and speed at every point on the surface of the planet. So electric fields, force fields, wind fields, these are different types of vector fields. It's basically tell me the magnitude and direction of some quantity at every point in space. That's what we're trying to do with electric fields. All right. So I think I said I was going to write something up here. Let's go back to our notes on the board. For point charge, the electric field is K Q R hat over R squared. And this Q, I'll put it Q subscript S. I'm going to call that the source charge. That's the source of the field. And that's to distinguish it from this one up here, which we gave a symbol Q naught, which was the test charge, the charge that will experience that field and have a force on it. And just like before in forces, we can avoid dealing with this R hat in this manner. Furthermore, I could get the magnitude only if I use the charge magnitude. Okay? And I just want to drive this home even more. The force uses a pair of charges. The electric field uses a single source charge. I'll call that Q sub S. Lastly, I know I mentioned this, but I want to say it again. I'm running out of room, so maybe I'll squeeze it in right here. if for some reason you have multiple charges, this was that superposition principle. The total electric field is equal to the first one plus the second one plus etc. So this principle is called the superposition principle. I'm going to write that down. Now, at first, you may be saying, this is silly. I learned forces well. I'm just going to always use this. It turns out in practice, this is a very useful mathematical tool, even though at first you're going to be a little bit annoyed by it. I want to point out a couple of things. Number one, the electric field only has one charge to worry about, so that's one less thing to think about. Number two, we know that the R vector, it's simple. It's from the source to the point of interest. So R is from the source to the point of interest, wherever we want to find the electric field. So if I want the electric field in Detroit and my charge is in Compton, the R vector would be the vector from Compton to Detroit. All right. So we're going from our source of the field to the point that we want to determine the electric field. All right. We'll do an example in a minute. But look at this. If you have a lot of different charges, it turns out it's very quick. Not very quick. It's relatively quick to get the electric field compared to the force. So what you can do is if you only care about the force on one charge in a problem, you get the electric field for every other charge, add them all up, and then multiply by the charge you care about. And it's slightly faster than getting the force. And more on that. There's other reasons this is a good idea. Okay. So same things as before. All of it is in the R vector. Watch out for the difference between magnitudes and vectors. And remember that when you're adding quantities that are vectors, you have to add the full vectors, not the magnitudes. Let's do, let's see, is there anything else I want to say? Oh, and maybe, yeah, let's just do it. Let's go do a problem. All right, so let's look at 22.2 on page 15. Okay. And so we have, oops, I need to scoot this over a little bit. We've got two charges on a grid. One of them is up here. And then maybe what I'll do is I'll make sure I'm using the same colors as my solution. Sorry, just a second. Forgot to bring that up. 163. Okay, so I'm going to use a red one up here. We're going to call that charge 1. And I've got a blue one over here. That's going to be charge 2. It's supposed to be the same height. Okay. All right, and so in this case, my goal is to, oh, and let's get the numbers. Making sure I got the numbers right. Sometimes doing a problem with numbers can really help you get a feeling for it. All right. And the question asks, sketch the directions of E1 and E2, and we want the field at the origin. So in part A, we want electric fields at the origin. All right. So we know the equation for one, electric field due to charge 1 or caused by charge 1 is K Q1 R1 vector over R1 cubed. Remember, you could do R1 hat over R1 squared or R1 vector over R1 cubed. Now, what is R1? R1 equals from Q1 to, in this case, we want the field at the origin. Our point of interest is the origin. So I want to learn about this point, the origin. So I go from Q1 to the origin. Now, later in class, you're going to hear me call this POI, or point of interest. That's just the term that I use. It's just because it's not always going to be the origin. We're going to go from Q to some arbitrary point that we care about, which I would call, in general, the POI. All right. Well, when I look at this, I know Q1 is positive. And I know going from Q1 to the origin is this way. I know the electric field should point that way. That should be E, whoops, I'm going to write on the other side. That should be E1. Now think about this. You can also think about it this way. If I put a plus charge here, the force would be downwards. That's a trick for getting the direction of the electric field. Pretend you put a charge here. Put a test charge here, and the test charge is always positive. So if you pretend there's a positive charge right here, there would be a downwards force from object 1. That tells me, my pretend charge tells me there's an electric field downwards there. Similarly, that is R2. I know that E2, I'll put this somewhere here. Right? Q2 is a negative charge. So I know it's going to point opposite this direction or opposite this vector. So I know that electric field 2 is going to point up this way. Now let's think. If you put a plus charge here, 2 should attract it. Therefore, the electric field would point that way. Again, the force caused by 2 on a plus charge at the origin would be this way. That means the electric field caused by 2 is that way. Again, the test charge is always positive. You think about the force, and that tells you the direction of the E. All right. So now, if we know E total is equal to E1 plus E2, I could do vector addition, and it's probably going to be what? Let me see if I drew it. It ends up being this way. It's probably going to be a little bit, so let's see, we go up here and straight down, so it's probably going to end right about there. I'm maybe not drawing this perfect, but we think this should be E total or E net. Again, the idea is we can get each vector separately, then add them together. That is the superposition principle. All right. So we can tell it's going to be, you probably recognize this problem at this point, but whatever. Let's actually get the net field and plug in some numbers and see if this makes sense. So, so this is B. We already did that. See the sketch. C is asking us to do We want to get the magnitude and direction. Okay, so in this case, I need to get the numbers for these and plug them in. And I think, if I'm not mistaken, R1 is going to be negative, let me read what it was. It's 4 centimeters, which is 0.04 meters. Again, we've got to use meters because the constant K uses meters, right? And then R2, this one is going to the left 3 centimeters. And down, let's put the meters out at the end so I have enough room. All right. So this one is going 3 centimeters left, 4 centimeters down. And so there's our 2 R vectors. At this point, you probably can see that 0.04 meters is R1, the size or the distance. And over here, this is a 3, 4, 5 right triangle, or you could do Pythagorean theorem. That's the distance involved. We have all the pieces we need to plug in these numbers. So let's actually do that. K is approximately 9E9 or 8.99 times 10 to the 9th. Let's keep the units for this one. Newtons times, what was it? Newtons meters squared over Coulomb squared. Remember, that's on your equation sheet. Times, well, let's just do it this way so it looks neater. Q1 is 1 times 10 to the negative 6th coulombs. I'm cutting sig figs just for space in the camera. We should technically include them all, but whatever. Being a little loosey-goosey here. R1 was, wait, R1 vector on the top. Oh, this was wrong. Crap. What did I forget here? J hat. So the vector has to be a vector. Negative 0.4 meters or 0.04 meters was a scalar. So without that j hat, I was wrong. We got it right on this one. We included the I hats and j hats on the vector. Here I just forgot. So I apologize there. Let's clean that up. And now I actually want to look at the units before I punch in the numbers here. Notice I have meters cubed and meters squared and meters. So the units of meters will drop out. I have meters cubed on top and on bottom. The coulombs do not completely cancel. I have 1 here, 2 there. So notice I get the electric field has units of newtons per coulomb, force per unit charge. All right. And after all that, I actually have the number written down here. I got negative 5.619 mega. So just for in the interest of space here, I punched in the rest of these numbers. You can take a second to do it. I said 5.619 meganewtons per coulomb. Was it negative j hat? So I'll slap the direction out here at the end, negative j hat, just get this rolling. Now you could do the same thing for E2, and when you plug in all that junk, well, maybe let's do that. Let's actually write this one out. It's the first one, right? This time I won't do the units because we know what they're going to turn out to be. We know the units are exactly the same. They should turn out to be newtons per coulomb. So 8.99 negative 2 times 10 to the negative 6, because it's micro. R2 vector was negative 0.03 I hat. Again, for this one, I know I'm ignoring the units since they're going to work out. That should be everything in the numerator. Oops, canceled out all the units already. We know what's going to work out. And this is what I wanted to point out. The R vector, everything's negative, right? We're going down and to the left. But the charge is also negative. And notice, because of that, the electric field points in the direction we expect. So you may have been worried, like, wait a minute, the R vector is pointing the wrong way. Or, oops, this charge is negative. Is that going to screw things up? If you trust the math, we know physically a negative charge should attract a positive test charge. And the math also shows that. Out of all this, just to save time, what did I get there? 43, 15, 57, 54. All right, I'm going to read that again. 43, 15. 5.754. Again, we get meganewtons per coulomb. So these numbers times 10 to the 6th. All right. Now, at this point, if I want the net field magnitude and direction, I do the same process as last time. I have to add the i's with the i's. I have to add the j's with the j's. And when I do that, what I'm saying here is I add the two vectors, then get the magnitude. And just to draw this out, right? The I hat part, this one has no I hat part. So I'll put a box around that so you can tell what I'm looking at here. And then I'll put a box around this one. So we're taking these two terms in a box and we're adding them together. When I do that, the E1 has no I hat, so this is the only I hat. And now the J hat is almost going to cancel out. Where'd my calculator go? So I've got 5.7 minus this. This was in the negative J hat, right? So 5.754 minus 5.619. 0.0135 or 0.135, excuse me. And now I'm going to notice I've been keeping track of the sig figs here. Assuming we used 3 on all these numbers up here, we would want to round in the third digit. That's why I'm showing this. Now here, when we're adding and subtracting, we keep the columns. So we are only good to the hundreds column. So this one's actually only good to 2 sig figs. If I want the magnitude of this, I know you may not want to do this, but why don't we actually draw this damn thing, right? Oh, and what did I forget here? Units. On test day, if you forget units, you can bet you're going to lose points. So, all right. We did not yet answer the question though, right? We got the units on there, but we've not gotten the magnitude and direction. So let's draw this stupid thing, right? It's got a large positive I hat and then a small, whoops, small positive J hat. I was wrong there. It goes a long way this way, a little bit up. That's not the scale, right? It's a lot. It's 43 times longer than it is tall, okay? Approximately. To get the magnitude, I treat this like a normal triangle. And then to get this angle in here, phi, this tiny angle, I can do tan inverse. So I'm going to do x squared plus y squared, then take the square root. So 40 or 4.315 x squared. Now you might be saying, dude, what about the megaunit? We can put the units on the final answer. Square root of that. 4.317. Since this is our final answer, maybe I'll write this and tell you how to put it on a test. Again, we should put the units. And on the test, you would probably round to 3 digits. So this is when you would finally round. If I want phi, I'm going to do tan inverse of punch it in. Now here, I might mention this one has 3 sig figs. This one has 2 sig figs. When you work this one out, this answer will have 3 sig figs because you're doing an addition after you square them. You square them, this one only has 2 sig figs, but then it turns out to be almost negligible. And so the sig figs are dominated by this term. In this one, we're taking a ratio. When we take this division, we should probably round this to 2 sig figs. So this is exactly the same charges as that problem we did in the last lecture. Charge 1 and charge 2, where one might remember this? This was problem 21.3. So this problem is exactly the same as 21.3 with one major exception. There's no charge at the origin this time. We were pretending there was a charge there. Now think, if you put a plus charge here, it would feel a force in this direction. In 21.3, we actually had a negative charge at the origin. So notice a negative charge feels a force opposite the direction of the electric field. The equation for the force on the test charge it's on any charge, right? Now we don't even need to say test charge. If I put a charge at the origin, I take the charge that I'm going to place at the origin, multiply it by E total, and that would give me the force. If you put in a negative charge, the force would be the opposite direction, just like we saw in 21.3. In fact, if you put in Q equals negative 3.00 microcoulombs, you will get exactly the same results as 21.3. And I worked this out in the solution so you can see it. So, all right. That's the basics of getting the electric field from 2 point charges. And then maybe let's go back and look at this board again and review some important stuff. The electric field uses a single charge. Electric force needs pairs of charges. Excuse me. The electric field can be thought of as the force per unit charge, newtons per coulomb. Okay, one charge creates the field, a different charge should experience it and have a force on it. If the charge is positive, the force will point in the same direction as the electric field. If the charge is negative, the force points in the opposite direction. For a point charge, here's our formula. And what is this R vector? Most of these problems come down to, can you do this correctly? So you need to understand the definition of it. It goes from the source to the POI, from the source to the point we're interested in. If I need just the magnitude of the electric field for some reason, some of it got erased by me bumping into it. Remember, you need to use the charge magnitude, just in case the source charge is negative. Finally, when we have multiple charges, use the superposition principle. Get each electric field from each source separately, then add them all together. Let's see if I want to do another one here. Yeah, let's do another one. Okay. Let's do 22.3. So you could take a second to look at that while I erase and get the board ready, okay? 22.3. I'll go like this one here, like that, so you can tell when I'm done erasing. Okay. All right, that's pretty good. Okay, let's redo another problem now, 22.3. And we're going to do this one. It's the same kind of stuff, but we're going to do it algebraically. All right. And so now, this is kind of a fun one. We haven't done one quite like this. It's similar to some other ones, but it's not exactly the same. Remember, you got the solution. So if you don't like my pacing, go ahead and work without me. Remember, sometimes it's nice to have a slightly bigger picture than you think you need. Ooh. This is the x-axis, and this is the y-axis. There's going to be some point up here. I labeled this point Z. I labeled this point P, just to give them names. So now instead of just having the origin, we've got the origin, we've got the point P, the point Z. These might be potential points of interest. We've got a plus charge. We usually use red for that. We've got a minus charge down here. Same distance, approximately. Okay. We're told that these are spaced by distance A. Oops. So that distance is A. Whoops. And I want to point out, we should take a little bit of care. A lot of you are pretty sloppy with your handwriting. That's fine. But notice we're going to have the letter Q and the letter A. And I know it seems simple, but you better make sure they look different on test day, or you might lose points, because I can't read your writing. You're going to lose points. So take a little bit of effort to write these clearly. And then down here, that's distance X. And finally, this distance here was y. Okay? So I just picked some random letters. And yeah, y might look like 2a, but to be clear, y is not necessarily equal to twice a. Y is just its own number. This could be 3, and maybe this is 5.7 or something. I don't know. Okay. Part A asks for the electric field at the origin. All right. So in this case, I'll say that E origin, just to give it a name, you could call it whatever you want, is equal to E1 vector plus E2 vector. Okay. Now in this case, what is E1? Well, that's going to be, and let me see, what are these charges? They both have equal magnitude. So maybe I'll put that here. Q1 is equal to Q, but Q2 is not equal to Q. It has the same magnitude, but it's negative. So here, the wording of the problem says the magnitudes of each charge was Q, and the picture tells us this one was negative. Combine that piece of information to get Q2 equals to negative Q. Okay. By the way, this is called an electric dipole. Just like a magnet has a north pole and a south pole, we can think of the plus charges like a magnetic north, and minus sign is a magnetic south. Magnetic fields point out of north and into south. More on that in the last half of the class. So this is called an electric dipole. Okay? Two charges, opposite signs, separated by a small distance. All right, so now I'm just going to rock this out. This is going to be K, Q1, over the distance cubed. Actually, well, yeah, let's do it. And now the vector going from here to the origin, that's the vector I need. The distance is a, the vector is a negative j hat. So if you're wondering where I'm getting that from, let me write down the general formula. The electric field is equal to K, Q of the source, times R vector divided by R cubed, or you could use R hat and R squared. And remember, R is from the source to the point of interest. From source to POI, you're going to hear me say that all semester. This is the source of the field. This is the point where I'm interested in finding the field. So I go from here to there. That's why I used negative AJ hat. Now I'm going to add the other term, E2. K, Q2, and I've got A cubed. And in this one, I go from source 2 to the origin, which is positive AJ hat. So what do you think? Are these going to cancel out? By the way, whenever I ask these questions in the video, I'm assuming that if you want to actually think for a second, you'll hit pause on the video. So let's ask that again. And if you want to, anytime I ask a question, hit pause and then I'll try and answer. That way you get a chance to think. In this case, are these going to cancel out? Yes or no? No. Q2 has another negative sign. And we see this is why these are more annoying than gravitation. You got to constantly be thinking about what is the minus sign associated with the charge itself. Cleaning this up a little bit, this is Q, this is a negative Q. One of the A's cancels in each term. And notice we get the electric field net is going to be, I guess I'm going to get they both will have a negative. There's two terms that have K, Q over A squared in the J hat. Well, how could we check that? Obviously, we could plug this into the computer simulation. But let's think. If I'm sitting right here, and again, I pretend to put a plus charge there. I put a fake charge called the test charge right there that's positive. If I put a plus charge here, I expect the plus charge on top should push down. I expect the negative charge on bottom to pull down. That's exactly what we just saw. If I pretend to put a plus charge here, both of these would actually exert forces in the same way. It's opposite side, opposite charge, same direction force. So this makes complete sense. We expect it to be twice as big as one of them in the negative J hat. I mean, that's perfect. All right. So that takes care of the origin. What do you think the next one is? At P. All right. Well, let's do our thinking this time. Sometimes if we think first, we reduce calculational effort. Well, if I put a plus charge here, actually, maybe I'll leave this other one here. I'll put that there, and we said there should be a red down and a blue down. Check this out. I know that the red one, if I put a plus charge at P, would exert a force this way. The blue one would pull it. Notice, I'm going to label this up top because it seems like that would be a more convenient way to do this. Notice we expect the I hat parts to drop out. We expect the I hat parts to drop out. So in this case, we expect the electric field at P net to point that way. Well, what I could do is I could get the electric field from either 1 or 2, get the Y component and double it. So let's do that. In particular, what I'm saying is E at P is equal to 2 times the J hat part of either one of these, but I guess let's maybe use the red one, E1. So if you don't want to write all that junk, why don't we just say this is 2 times E1 Y vector. So you got to remember to include the J hat when you write it. That's what that vector means. Okay. So what is E1? In this case, what was this distance? X? So this vector should equal X in the I hat minus A in the J hat. Let me see if that's right. I just kind of write it down and then check it. I'm going to go I hat, positive I hat X, and then A hat down. Yeah, okay, that looks good. And so notice R1 magnitude that. So now it's actually easy to write this down. Q1 is Q. Q1 is Q. This was raised to the 1/2, and then remember, you got to cube it. So the distance was to the 1/2. When you cube it, you get 3/2. And if you ever have trouble with the math, like you might be saying, oh, you're doing this too fast, I don't know how you get there. Just talk to me in office hours or in class, and I'll show you more steps if that's what you need to succeed. I have no problems with that. So for real, just talk to me, all right? All right. Next, I need to get just the j hat part and double it. So the j hat part, we're going to kind of cancel out this part. We don't need this, but I do need the minus sign. So this is going to equal, the 2 comes from the symmetry, seeing that the I hats cancel and the j hat gets doubled. I get a k, q, a, j hat, and there's a minus sign. I just moved the minus sign out front just to make it look pretty. Like that. Okay. So that's part B. And notice, yeah, these are slow when you first get started, but after a while you learn some tricks. So if you're doing the homework, when it comes time to practice for the test, it won't be as onerous. If you don't practice, you are going to be so slow you fail, right? It's not, I'm not trying to be mean, I'm just trying to be honest, that if you don't practice a little bit before the test, you're just going to be awful and you're going to be miserable. Whereas if you do practice, yes, it sucks, but you get that part out of the way before test day so that the tests don't suck. All right, you got to practice in this class. It's not like you just cannot get away with not practicing anymore. You have to be practicing to be any good. All right, finally at Z, maybe I'll leave that one for you at home, but let's think about it. What direction do you think the electric field should point at Z? Do you think it'll cancel? Do you think it'll be upwards, downwards, right, left? So again, take a second to think, if you want to pause the video, what direction and size do you think this might be? Do you think it'll be big, small, up, down, right, left, angled? What? Pause the video and think. Okay. Well, I know that the plus charge should exert an upwards electric field. Now, how do I know that? Pretend you put a plus charge here. Remember, the test charge helps you think it through. Pretend you put a plus charge here. We know there'd be an upwards electric field. Now, this minus charge is hella far away. That's going to be a downwards field, but it should be a lot smaller. So in the end, I expect these do not exactly cancel out. I do not have good symmetry here. I can't just guess and say the answer is 0. I do expect the plus charge, the closest charge, should probably dominate, and I think there's going to be an upwards electric field. So now you have to be a little bit careful here. This is a very common math situation. Notice that this, you'll see this all the time. This distance right here is not y. It is not a. What is the distance? Y minus a. How about over here? This distance is going to be y plus a. And so a lot of problems will have this scenario where one of the distances is y minus a or x minus a or d minus x or something, and the other one has a plus sign in there. It's very common, especially with dipoles. All right. Good. I want to sketch out another one for you. I didn't do all of that one, but let's at least look at it. Come on. Oops, let's get the globe out of here. Right. I want to look at 22.4. This is kind of getting serious now. My goal here is to sketch this out and try and give you a feeling for it so that you can work on it on your own and check it against the solution. So in this problem, we have 2 point charges. This is 30 degrees. Excuse me. and the distance is d. This one also has distance d, but the angle is 45 degrees. Okay? We're assuming that this is the x direction, and this is the y direction. The white charge is negative with unknown magnitude, Q. So this one is negative, and this one over here is positive. We've got a negative charge and a positive charge. Oops, let me write this in a different color. So to keep this problem doable, what we're doing is we're saying there's a charge magnitude Q, so everybody labels it the same way, but Q is not known. We do know basically that this one is negative and this one's positive, and that this one is twice as big. So this is negative Q, and this is positive 2Q. Let me make sure I got that right. Yes. All right. Finally, some sensor is used, and we know the electric field magnitude. So it's a variation. Previously, we knew the charges and we found the electric field. In this one, let's say we know the electric field using a sensor, and we're trying to figure out these charges. We don't know the actual amount of charge, but we do know that they're opposite sign, and this one's twice as big, and we know the angles and the distances. All right, what are we trying to find? Okay, so part A says, we know the size of the field, determine the direction at the origin. Now, typically, when I ask you for a direction, I'm expecting an angle, usually a number. So I'm looking for a numerical value of the angle there. All right. Part B says determine Q. The unknown charge magnitude. What should we do? Well, at this point, we only have one trick. This problem at first to a lot of students seems impossible. The trick is the following. Do exactly the same thing we've been doing all day. Assume you know what Q is, work the entire problem out, and in the last line, we know the electric field magnitude. We're going to follow the same steps that we would anytime to get an electric field magnitude. Namely, we're going to say E total vector is equal to the sum of the two parts. In this case, 2 is the red one, and 1 is the blue one, because 1 was negative and 2 was positive here. Once we do that, we can take the magnitude of this equation and solve it for Q. Or we could also get, maybe you recognize this, E total is going to end up being some amount in the X. And I guess you could probably think it through whether it's going to be plus or minus I hat. But for now, let's just do this. Right? Maybe let's try to think it through. These charges are the same distance away, but this one is twice as big. So in this case, I expect at the origin, that arrow and this one half as big. Well, in this case, I could do a parallelogram rule. I can tell the net field should be, oops, I've been using green. I can tell, look, this one's going to pull down and be half as strong. This one's going to push away if I put a plus charge there. So I can tell that the net field by the parallelogram rule, I'm going to draw this one too, should be that way. I know that's the electric field. Well, if I do this, I could actually rewrite this. Should be negative or I guess I could say it like this. E total X is going to be in the negative I hat. That's going to be a negative number. Right? And I'm just trying to think this through to get a feeling for it before I waste my time. Well, if I draw this picture, I guess I don't need absolute values there, but don't need absolute values in here because when I square them, again, I don't really need the absolute values here, but I'm treating this like a triangle. So if we walk through the equations and just plug in the same junk that we've been doing all along, we're going to work through all this stuff. And notice when you plug in the numbers here, there's going to be a Q in the numerator and a Q in the denominator. It'll drop out and you should be able to get a number for the angle. And then finally, because we know the field magnitude that was given to us, this equation will be one we can use to solve for Q. So we're not doing anything different. It's just a question of you have to stick in an unknown parameter and then later on solve for it. I hope that made some sense. You should work through this one. Same procedure, the superposition principle over and over and over again. And then the question just becomes, what do I ask you to solve for? So hopefully that makes some sense. All right. And then maybe I'll point out, let's look at 22.5 really quick. 22.5. So I'm going to leave the rest of 22.4 for you to do. And to do 22.5, I think the simulation is where you want to go. And maybe I'll try and remember to put this simulation in here. Let me screen share real quick. Let me clear everything. We'll put a grid up here. So again, I'll try and put this link to the simulation in there, or you can screenshot it or whatever you got to do to get this done. So the reason I want to do this problem is the following. over and over again, we've seen situations where symmetry may be useful. And it's important to learn how to analyze problems to discuss if symmetry will help or not and save you time on test day, right? It also helps you reduce mistakes in making calculations. So let's do one of these scenarios that's shown in 22.5. Let's make a rectangle. Here's one, and I'm going to put a plus charge here and a plus charge here. And then down here, I'll put a minus charge and a minus charge. So again, just to make clear, what am I doing? This is problem 22.5. In my book, it's on page 16. Okay. So now we're wondering, it says, sketch the electric field at the center of the rectangle. Oh man, maybe I should make this, I should figure out where the center of the rectangle is. Tell you what, if I just move these up, let me see if I got this right. So I go 1, 2, 3, 4, 5, 6. So it's on this line right there. I think that white dot should be the center of the rectangle now. And again, I didn't draw these perfectly. The charges aren't perfectly placed, so I apologize if this isn't exact. Maybe I'll try and improve it just a little bit. So that's pretty much right on the vertex, approximately on the vertex here. That's as close as I can get it, I think. All right. So where's the electric field at the center? Take your guess. Or maybe I'll show you what I would do in my mind here. Look, these charges are all equidistant from the center. So I'm going to go through these one at a time. So here's one. One is going to push. So I'm going to draw a little arrow and draw one. This is charge 2. 2 is also going to push if I put a plus charge there. Okay. So again, we're looking at the electric field, but we pretend to put a plus charge at the origin and then think, okay, if I pretend to put a plus charge there, which direction would the force be? That direction is the same as the electric field. Finally, let's say this one's 3. Well, that one's going to pull. And 4 is also going to pull. So when I look at that, I could tell by symmetry, the I-hats all cancel out. The net force on a plus charge at the origin should be downwards. That means the electric field at the origin is downwards. So by drawing those little arrows and just thinking it through really quick, put a pretend plus charge at the point of interest, we're good to go. Well, let's try this. Let's have some fun here. Let me get my eraser out. Sorry. Let me move this out. Whoops. And then, sorry, I'm a little slow here. Let's have some fun. What if instead my point of interest was right here? Well, let's go through this. This one's a hard one, okay? Oh, whoops. This is actually similar to 22.6, but whatever. It's not exactly the same, so it's fine. 1 is going to push. You think. If you want to pause the video, this is a good time. Think. Take a second. Where would the electric field net be at that white dot on the screen? All right, here we go. 1 is going to push if I put a plus charge there. 2 is going to push, and it's going to be smaller. It's farther away. 3 is going to pull straight down. Hey, that looks a lot like the problem we just did, doesn't it? So that's 3. This is 4. 4 is going to pull, but it's going to be weak. Whoa, that one's also going to be straight down. Do you agree? So in this case, it's also straight down. So you could go through this and practice at any side of the square, at the center. There's a couple other ones you could try. I wrote these up in the solutions just like this, so you got a lot of that going on. All right. All right. And then I guess, let's see, how am I doing on time here? Yeah, let's leave it at that, and then I'll probably just have to stop and make another video later. So this wasn't quite a full lecture, but it's good enough to get you started on some of the stuff. I'll just have to make a second video. That way I'm not rushed.